Hello, this is Mr. Martin, and again, we are going to be talking about the volume of solids of revolution today. So, to get started, let's take a look about what today's task is. It's to find the volume of the solid created by rotating the area between the graphs of y equals x and x equals y squared. Now, these are two very familiar graphs to everybody, and I've drawn out the graph was pre-printed, but I notice I have some ink up here. And notice what we have. We have the graph of y equals x and the graph of y equals x squared. And the area in here that you can see is going to be rotated about the x-axis. So it's right around here. It's going to go out and back into the board. And it's going to create a kind of a bowls tape thing with the very outside edge being the graph of y equals x and the inside graph being the graph of y equals x squared. So if I go to the next page, I have the same graph drawn just in a smaller version. So when we're looking at trying to find the volume of something, and in this case we're going to be using what's called the washer method. And the washer method basically is picture this area here. When it gets rotated around, it's going to be that far on that side of it and that far. So it's going to create a kind of a washer kind of effect. Now my drawing isn't the best, but as it rotates, think of it, it's going to have a hole in the middle of it, and it's going to have a big outside edge. But if we were to find the area of a washer, I'm going to go to the next page here for just a second. If you look at this washer with the same kind of thing, notice that the washer is going to have, a washer would have a width W and an outside radius and an inside radius. Now, in our case, when the line is rotated, the outside radius is governed by the y equals x, isn't it? That's going to give you the outside radius. The inside radius is governed by the equation y equals x squared. So the difference in those, the outside, if I take the volume of a cylinder that's outside and subtract out the little hole, the donut hole, I should get the volume of that washer. And of course, since we're in calculus class, what we're going to do is end up summing those a whole bunch of little washers all the way from 0 to 1. So let's go back to the previous page and see if we can do an equation. So first of all, we want to know what R1, or the outside R is. So R, we'll call it R2 is the outside, equals, we're going to get it from the equation y equals x. So the y value is just happens to be whatever the x is, doesn't it? So it's just going to be x. R1, the inside, is going to be governed again, as we said, by y equals x squared. So whatever R1 is, it's going to be x squared. Well, we know that the area of a washer is just pi r squared, don't we? So if I were to, wanting to find the volume of this, I would take the integral from 0 to 1, because that's where the points of intersection occur, of pi times the big R, which is x, squared dx. That's the area of the big washer, minus the integral, the sum of the little ones, of pi x squared squared dx. And what I can do now, of course, is I can integrate this. I'm going to rewrite this really quickly as integral from 0 to 1. So it's pi x squared minus the integral of 0 to 1 with the pi on the outside of x to the fourth dx and dx. Now if I go ahead and take the definite integral of this, since it's both 0 to 1, I'm going to just rewrite that as pi x cubed over 3, evaluated between 0 and 1, minus pi x to the 5th over 5, evaluated from 0 to 1. And of course, these zeros are going to drop out, so over here I'm going to write the entire answer as pi x cubed, but x is 1, but let's just do this, minus pi x to the 5th over 5, both evaluated between 0 and 1. And just doing the math now, putting 1 in, I have what? Since 1, I have pi over 3 minus pi over 5 is the volume of the area when it's rotated about the x-axis. So that's it for that particular problem. And we are going to add